Definitely for this one, the irrational numbers. What else can we not have? Yeah. What's that? We can't have negatives. So this is not a group, this is not a set of numbers that we talked about, right? This is just now we're talking about numbers that we obviously can't have. The answer to this problem, though, is the irrational numbers. We can't have irrational numbers. I can't say that I can't have rational numbers because then that would mean that I can't have any numbers at all. I can have rational numbers. I can have integers. I can have whole numbers. But mostly if we're talking about people who entered a race, we're talking about natural numbers, right? Okay. So no negatives either. And no fractions. By fractions, I mean like 1/4. Clearly, you can't have 1/4 of a person. Okay, let's just go ahead and keep moving on. Graph the numbers on a number line. Do we know how to draw a number line? So this is kind of a review, right? Even though we're still in section 2 already. Chapter 1 pretty much does a lot of reviewing. So, graph the numbers on a number line. We draw a number line. And we should probably figure out what the leftmost number and what the rightmost number need to be. So what's the most left number that I need to put on this number line? -3, I like it. How come -3? -5/2 is to the right of -3, all right? I don't have to put exactly those numbers that you see. I want to make my scale work for the numbers that I'm going to be putting on the number line. And that's all I'm working on right now is scale. So what is the rightmost number that I need to put on the number line? Yeah, how about +3? I know 2.6 repeating is to the left of +3. Do I know what the square root of 2 is? Is it bigger than 3? No. So definitely +3 is going to be good enough. Okay? Now fill in that number line. In the middle we probably have 0. So I'll put a 0 there. And then I also have -1, -2, +1, +2. So there's my number line. Okay? Where's root 2? That's a good question. Now we're going to put the numbers on the number line. So set the number line up first. That's what I'm trying to tell you. And then put the numbers on the number line where they belong. Okay? Can we put -5/2 on the number line pretty easily? Yeah, where does it go? Between -2 and -3. That's a good spot. So like right here, right? Try to make it directly in between because -5/2 is actually what as a decimal? -2.5, and 0.5 is directly in between, okay? Is it going to be perfectly exact? No, because we're not using like industrial calipers or anything to really measure this out really well. You guys know what calipers are? Probably not. Blank stares. We're not using a ruler. We're just trying to make it as accurate as we possibly can given our limitations as sketchers in this class. And I'm going to write -5/2, and notice how I'm doing that. Yes, I'm using a different color. Don't have to use a different color. Put above the line, and then I can tell the difference between my number line and its scale and the number that I'm actually plotting. All right, 2.6 repeating. That one's probably an easy one to graph. Where should I put that? In between the 2 and the 3. Right there. Almost all the way over to the 3. Right there. Because 0.6 repeating is just a little bit more than half. So I'm going to go to half and then go a little bit more than half and call that, as accurately as I can, 2.6 repeating. Everybody knows what that bar above the number means, right? Doesn't stop. That number just keeps going again, over and over. So is 2.6 repeating a rational or an irrational number? It's rational. It has a repeating fraction. It has a repeating decimal to it. The last one we need to worry about is the square root of 2. You all came through geometry already. So what is the decimal of the square root of 2? No? This is something you should know. You should know what the decimal of the square root of 2 is, just as quickly as you know what the decimal of the square root of 9 is. Okay? The square root of 9, of course, is 3. The square root of 2 has a decimal that gets used again and again and again in math. You used it all year last year. Well, maybe not all year, but you used it a lot last year, whether you knew it or not. And it's something that you should know. What is it? Somebody who has a calculator in front of them, because your job when you come in here is to grab your calculator and go sit down, is what? 1.414 is what you need to know. Okay? This is something that you should know. The square root of 2 is rounded, 1.414. So where does 1.414 go? Almost halfway. So between 1 and 2 is 1.414. 0.414 is not quite 0.5, so here's 0.5, let's say. And I'm just going to back that off a little bit and put my dot right there. And that gives me my what? Square root of 2. Good. I'm not writing 1.414 because that was not the number that was given to me. I'm writing the square root of 2. I found out what the decimal was so that I could place the dot. Okay, so now we're going to compare two numbers using, what are those symbols? Which one's which? This one is less than, this one's greater than. The alligator eats the bigger thing, right? But you also need to know how to read it. This symbol always says less than. This symbol always says greater than, as you read it from left to right. Because this thing over here on this side will be smaller than this side. So you're saying this thing is less than this thing. Got it? Try to get away from the alligator eating something bigger. Try to think about it as I read it from left to right, it's actually showing me this point is smaller than this gap right here. So read it that way. Okay, so we're going to compare using greater than or lesser than. Use known values to help you choose the correct answer and explain your reasoning. By known values, I mean this. Do I know what the square root of 17 is? No. And I don't have a calculator sitting in front of me, said 18 people in this room. So we have to figure out how to do this in our heads without using a calculator, using known values. So I have this 3.8 sitting here. I know what 3.8 is. I don't have to worry about that, all right? Do not enter this into a calculator. Okay. The square root of 17. What is the square root of 17? Quick, to 3 decimal places. We don't know, right? Is it bigger than 3? Is it bigger than 4? How do you know it's bigger than 4? Right, the square root of 16 is 4. So therefore, the square root of 17 must be slightly bigger than the square root of 16. So therefore, the answer must be slightly more than 4, okay? Maybe it's 4.1, maybe it's 4.2, I don't really know. Does it matter in this case? No, because already we know that it is bigger, greater than 3.8, right? Go ahead and type in the square root of 17. What do we get? There you go, okay? That's using known values. So let's see if we can come up with this one on our own. All right, so we want a known value here, because I don't know what the square root of 26 is. What is my known value? We have the 6.25, and we don't know if this is greater than 6.25 or less than 6.25. What value should I use? Okay, the square root of 25 is 5. Is this the square root of 25? No. Is this bigger or less than the square root of 25? It's bigger. So if I have 5, and I need to go bigger than 5, do I know for sure where it stops? Do I know for sure if this is greater than or less than 6.25? No, I don't, actually. There's a better known value to use here. 36. What's the square root of 36? 6. Is that going to be less than this? So therefore, the square root of 36 is less than this, right? Is the square root of 26 less than the square root of 36? Yes, so therefore my answer is less than. Pick the right known value. You guys weren't far off, and yeah, you could say, okay, I have the square root of 25, it's 5. The square root of 26 is very close to the square root of 25, so I'm going to assume. But the problem is you're assuming, and you can't do that in math. All right? What if I had made this 5.25? Now you're going to struggle. So you'd have to figure that out a little bit differently. Anyway, that's comparing numbers using greater than or less than using known values. Let's take a look at the bottom one. Let A, B, and C be real numbers such that, what does that say? A is less than B and B is less than C. How do A and C compare? I want you to think about this for 5 seconds. What'd you guys come up with? A is less than C, right? I mean, that's logic, isn't it? If A is less than B and B is less than C, if I were to put those on a number line and arrange them, then A must be less than C. That is the only thing I can conclude from this statement. So how did you explain it? Okay. So in words, you could say it like that. You could put it on a number line. Yeah, I kind of gave you 2 hints on how I wanted that question answered just then. You could put this on a number line, okay? You have A is less than B. So here's A, here's B. Then over here you have B is less than C. So if B is here, then that means C must be somewhere over here. Okay? This is a perfectly acceptable explanation for why you can conclude that A is less than C. The number line shows me in a picture instantly. You want to put it in words? Go ahead and put it in words. But the picture shows it right away. And that's why in your word wall, I'm always telling you, try to come up with a picture that shows it, like instantly, because it's so much easier if you have a picture. Just continuing the review with the section, additive inverse and multiplicative inverse. These guys do something to what you're looking at to make something specific happen. The additive inverse, anybody remember that one? No, that's a property, yeah. A plus negative A is the example. A plus negative A equals what? 0. So can we come up with a definition now? Two things that add to make 0. That's not the formal definition, but it's a definition that works. Also known as is what AKA is. Do we have a word? A word? No. It's not property. Do we have a word that describes A and negative A? 4 and negative 4, opposites. Two numbers that are opposites are additive inverses. If you add them together, you get 0. Multiplicative inverse is very similar, except this time when we multiply these two numbers together, we get, we get 1, yeah. So if I have A, I will have to multiply A times what so that I wind up with 1? No, that would give me AB. A times 1 is A. A times B is AB. A times 0 is 0. A times negative A is negative A squared. None of this is giving me 1. 1 over A. A times 1 over A gives me A over A, and anything divided by itself is 1. Okay? So multiplicative inverse is two things that multiply to make 1. Also known as reciprocals. If two numbers are reciprocals of each other, they will multiply to give you 1. That is what a multiplicative inverse is. All right, normally I don't do this to you, but we do have some properties here that we need to review. We have the closure property, which you may not have learned before. The closure property simply says that if I have two things that are existing in a set of numbers, and I add them together, or I multiply them together, I will wind up in that same set of numbers. Okay? So if I add two real numbers, I get a real number. For multiplication, if I multiply two real numbers, I get a real number. That's all we mean by closure. The commutative property, so now we are talking about properties here. Anybody remember the commutative property of addition? If I have 2 plus 3, I can switch them and make 3 plus 2. We're going to write that algebraically, though, as A plus B equals what? B plus A. And now the commutative property for multiplication would be what? A times B equals B times A. You can reverse the order of addition and multiplication. The associative property is the one with parentheses. Anybody remember that one? We're not multiplying though, so we're not distributing. We're just adding. I have A plus B plus C, and let's put the B plus C in parentheses. Because it's all addition that we're doing here, the associative property tells us that we can add this in any order that we want. So this, according to order of operations, is telling me to add these two first and then to that. But actually, I can add these two first and then add that. I can add in any order I want. That's the associative property. Generally, if you see parentheses, that kind of means you're using the associative property. A plus B plus C. This is a plus. Sorry. So therefore, multiplication's associative property would be what? A parentheses B times C equals AB times C. You can multiply in any order. As long as it's all multiplication, any order is fine. That's all that says. Identity for addition. Identity means if I do something and I get exactly the same result back, then what I've done is an identity. So if I'm adding two things together, what would I have to add? 0. The additive identity is 0. The multiplicative identity then would be what? 1. Good. A times 1 gives me the exact same thing back. You probably used some of these properties when you guys were doing like chapter 4 or whatever it was in geometry when you had all those proofs. Best chapter ever, right? It's my favorite. I love that chapter. Inverse property. So inverse maybe means opposite? Maybe. Kind of maybe. Keep thinking. You're fine. The inverse property is like the additive inverse property. We just talked about it. That's all it is. If you go back to the previous page, additive inverse. So the inverse property of addition is A plus negative A equals 0. And the inverse property for multiplication is A times 1 over A gives me 1. Yeah. What is anything times 0? 0. This doesn't do me any good. I just wiped out the problem, okay? What I'm doing is I'm just turning this into something that is very basic. In addition, the most basic number we have is 0. In multiplication, the most basic number that we have is 1. If I take 0 and add it to anything, I get the same thing back. If I take 1 and I multiply it to anything, I get the same thing back, okay? So that's my identity property. The opposite of that is the inverse property. So I'm basically just undoing the identity property, okay? That's all it is. The distributive property does not exist in both. It exists in both at the same time. The distributive property is A parentheses B plus C equals AB plus AC. Okay? This is all one thing here. There's a line on the table, and that's my mistake. So those are your properties of addition and multiplication that you need to have like on the tip of your tongue at all times. You need to be able to use these constantly. I'm not going to ask you by name most of the time, but you need to know that they exist. All right, moving on. Which property does the equation illustrate? We have negative 2/3 times negative 3/2 equals 1. What is that? Which inverse? Multiplicative inverse. Or you could say the inverse property of multiplication. How about the next one to the right? 3 times g plus h plus 2g equals 3g plus 3h plus 2g. What is that one? That is not commutative. That is not associative either, actually. That is distributive. So just because you see parentheses doesn't mean it's automatically the associative property. Notice we have the 3 here, and then over here we have the 3 on the g and the 3 on the h. I kept the parentheses in there, but it's just the distributive property. Oh, okay. So the second one then, Kenzie, is what? Seems like it, doesn't it? Because I got those parentheses in there. But look at it. Like, really look at it. What happened? All I did was swap the 3 and the 4. Okay? We have 3, 4, 5. Here we have 4, 3, 5. So really what property happened here? The commutative property. The associative property would have been if I had 3 times 4 times 5, and over here I wrote 3 times 4 times 5. There I'm grouping differently. Here I'm just switching the 3 and the 4. Okay, use the properties of real numbers to show that a plus 3 plus negative a equals 3, and then justify each step. So this is what we call an algebraic proof. Don't grumble because you hear the word proof. Really all you do when you're solving problems is a proof. You're just not making it very formal. A proof is just a formal way of solving a problem. That's all it is. Okay? But you have to write down step by step by step. So that's what we're going to do here. Do we need to make a table? Steps and reasons? No? I don't think we do. Let's just go ahead and do this. So our first step, if this was geometry, would be to rewrite this step and then say given, right? Okay, so that's what we're going to do. A plus bracket 3 plus negative a equals 3, and that is step 1. Step 1, given. When it says justify each step, this is what you have to do. It's kind of a proof. Actually, there's no kind of about it. It is a proof. Okay, so step by step now, using these properties, we can all see that a plus negative a is going to be 0, and I'm going to be left with 3 equals 3 here, right? We all know that that's how we're going to wind up. But we have to get there step by step by step using these properties. And that's the hard part. So that means that we have to get these two things next to each other somehow. Can I do that? These are grouped. So you want to take this thing outside of the group and put it inside the group. Can we do that? What's that? Move the brackets. Can I move these brackets? Is this all addition? If I move the brackets, I'd be using what property? The associative property, right? Would that put the a and the negative a next to each other so that I can get them to add together? I'd just be moving the brackets. So should I do something before I move the brackets? What? Well, I thought maybe you knew why. Oh, okay. You had a 50-50 shot, and you were right. Flip the a and 3, yeah. Can I switch the place of these two? What property would that be? Commutative. That's what we need to do. So next step, number 2, a plus the bracket, and now I'm trading the negative a plus 3 equals 3. And we called that what? Commutative. Property of what? Addition. We have to be complete. It's not just commutative, it's commutative property of addition. All right, now we almost have these two things next to each other. They are next to each other, but they're separated by that grouping symbol. What can we do? Now we can move the grouping symbol. And we'll have grouping symbol here, a plus negative a, and then the plus 3 equals 3. What allowed me to do that? Associative property. Please abbreviate appropriately, if you abbreviate. Associative property of addition. All right, now what can we do? Now we can add the a plus negative a, and that gets us 0. So now we have step 4, in the bracket still, 0 plus 3 equals 3. And what property allowed us to do that? That is the inverse property of addition. Very good. Notice I did write that 0, okay? Because now I have to show this right here. What is this? 0 plus 3 is 3. So now I have step 5, 3 equals 3, which is what we were looking for, right? Show that this whole thing equals 3, so I proved it. And what step allowed me to do that? The additive identity property. Or you could have written the identity property of addition. Same thing. That completes the proof. This is a proof. It's an algebraic proof, but it is a proof. All right? And it's not that big a deal. You just got to go step by step.